Okay, we want to talk about graphing rational functions. On page 308, there's a procedure for graphing rational functions. And we're just going to do one. So example 7. Graph. They give us the function f of x equals x plus 3 over x minus 2. X plus 3 over x minus 2. Well, the first thing they say on page 308 is the y-intercepts. So number 1, y-intercept. If you want a y-intercept, you let x be 0. Okay? If you put a 0 everywhere the x is, you just have 3 over negative 2, so y equals negative 3 halves. So 0, negative 3 halves is my y-intercept. Okay? Second step they say on page 308 is the x-intercept. So 2, x-intercept. If you want an x-intercept, you let y be 0. They're opposites. If you want y-intercept, you let x be 0. If you want x-intercept, you let y be 0. So if you let y be 0, remember y is the same thing as f of x. You'll have 0 equals x plus 3 over x minus 2. Multiply both sides by x minus 2, so really you're just solving this. And so x equals negative 3. So negative 3 comma 0 would be your x-intercept. Okay? Then they say identify any vertical asymptotes. Vertical asymptotes. So vertical asymptotes. So the vertical asymptotes, since the numerator and denominator don't have any common factors, the vertical asymptotes will be exactly where your denominator is 0, so x equals 2 would be your vertical asymptote, because 2 minus 2 would make a 0 here. So x equals 2 would be the only vertical asymptote. Number 4 says determine whether you have any horizontal or slant asymptotes. So 4 is horizontal or slant asymptotes. Okay. Well, to find the slant or horizontal asymptotes, we'll start with horizontal. To find the horizontal asymptotes, if you remember, there was a set of steps that was on page 303 for finding horizontal asymptotes. Since the degree of the numerator is the same as the degree of the denominator, we'll take the ratio of those coefficients. There's a 1 in front of this x, and there's a 1 in front of that x. So 1 over 1 makes y equals 1. So y equals 1 is the horizontal asymptote. Okay? Y equals 1 will be the horizontal asymptote. Well, you'll have a slant asymptote exactly when the degree of the numerator is exactly one more than the degree of the denominator. So there are no slant asymptotes. Okay, there won't be any. Okay, there are no slant asymptotes. Then they talk about symmetry. You can apply symmetry if you want to. This thing will be neither even or odd. Okay, it won't be even, or odd. Oh, wait a minute though. Is it going to be? Yeah, it's neither even nor odd. Okay, and remember the test was you put a negative x everywhere the x was. Okay, if you get the original function back, that means it's even. If you get the opposite of the original function back, then that means it's odd. So this thing is neither even nor odd. So 5, no symmetry. Okay, and then number 6, again that list is on page 308, and 6, my number 5 is their number 6. And then they say plot other points, and I'm just going to say 6, plot more points. Okay, once you've done that, you've got all this information. Let's just plot a few points and see if we can actually come up with the graph. All right, so this over, see if I can graph it. And I do apologize for my temporary. The next video I do will be a little better than this, so bear with me, please. Okay. So again, remember the function was f of x equals x plus 3 over x minus 2. Okay. So we had done some things. We had an x-intercept at a y-intercept rather at 0, -3 halves. So let's just go ahead and see if we can plot the information that we've already determined. Okay. Let's see if we can plot the information we've already determined. So there's my x-axis. There's my y-axis. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Okay. We said we had a y-intercept at 0, -3 halves. That's right here. Okay. We said we had x-intercepts. The x-intercept was exactly when x was -3. So the -3, there's an x-intercept. Okay. We said we had a vertical asymptote at x equals +2. So here's my vertical asymptote. There was a horizontal asymptote at y equals 0. So really, the horizontal asymptote is, no, the horizontal asymptote was y equals 1. So y equals 1 was my horizontal asymptote. Okay. So we got a little bit of the graph. So the general rule is when you can't tell what's happening in a region, just get some more points. So for instance, it kind of looks like the function is doing this, but if I'm not totally sure, I can check x equals 1. I can just calculate a t-chart. If x is 1, then f of 1 would be 1 plus 3 over 1 minus 2. That's 4 over -2. That's -2. So 1, -2 is on the graph. So I go over 1, -2, like here. So I really don't have a choice on this function. Since this is an asymptote, as this is an asymptote, the function is going to have to do this kind of thing. Okay? Now, I don't know what's going on over here. So whenever you don't know what's going on in a region, that just means you need to get some more points in that region. Okay? So I need to choose maybe x equals 3, 4, and 5. So 3, 4, and 5. Find f of 3. That's 3 plus 3 over 3 minus 2. That's 6 over 1, and that's 6. So 3 comma 6. 3 comma 6 is on the graph, somewhere up here. Okay? F of 4. So I'll put a 4 everywhere the x was. 4 plus 3 is 7. And then the bottom, 4 minus 2 is 2. That's 3.5. So 4, 3.5, about right here, I don't know. Then do 5, f of 5. Everywhere there was an x, put a 5. 5 plus 3 is 8. 5 minus 2 is 3. So 8 over 3. 8 over 3, 3 goes in 8 twice, right? So 2 2/3. So I go over 5, 2 2/3, about right here. So I really don't have a choice. This thing is going to have to kind of do this. So there's my graph. So that's how I'm going to graph these things. I'm going to plot my y-intercept first. I'm going to plot my x-intercept next. I'm going to find out any vertical, horizontal, and slant asymptotes. Then I'm going to put all that information on my graph. And if I don't, and I can also use symmetry. And if I don't see what the graph looks like, all I'll ever have to do is just get a few more points, and that'll always fully determine what the graph is. Okay? That'll always fully determine whatever the graph is. If you don't know what a function is doing in a region, do a t-chart and get points in this region. Choose those x's that are in that region, put it back in the original function, and then you'll be able to determine what the actual function does. Okay. I'm going to skip example 8. Okay. I'm going to skip example 8. I'll do example 9. Okay. I'll do example 9. Example 9. Graph. They say 2x squared minus 3x minus 5. X squared minus 3x minus 5 divided by x squared plus 1. Okay? I want to graph 2x squared minus 3x minus 5 over x squared plus 1. Okay? Well, I'm going to follow those same things. So y-intercept. The y-intercept is what I'm going to do first. So again, become familiar with that list of steps that are on page 303 because it's going to be important to do all those steps. So it's perfectly fine. I don't need you to memorize that list. I just need you to be able to use it if it's given to you. So number 1, y-intercept. The y-intercept, you let x be 0. That was 3x. So everywhere I had an x, so let x be 0. Everywhere I had an x is a 0, so that goes away, and that term goes away, and I'm left with negative 5 over 1. So 0, negative 5 would be my y-intercept. 0, negative 5 would be my y-intercept. The x-intercept, where x-intercept, you let y be 0. So again, whenever you're solving a rational equation, you set it equal to 0, really all you're ever doing is setting the numerator equal to 0. Okay? Whenever there's a fraction and you set it equal to 0, we said to do the x-intercept, we let y be 0. So where the y was, y is f of x, I put a 0. And it's always going to be the case that the numerator is what you're going to be setting equal to 0 and solving. Because when I say 0 equals 2x squared minus 3x minus 5 over x squared plus 1, if I multiply both sides by x squared plus 1, then the denominators go away. So really I'm solving this. So maybe we can factor this thing, 2x squared minus 5x, or minus 3x minus 5. So let's try to factor it. So 2x and x. I need a 5 and a 1. Okay, and I want that to be a minus, and I want that to be a plus. So there's the factorization. Okay, there's my factorization. Well, I need to solve. I've got a product equal to 0, so either this one is equal to 0, okay, which says 2x equals 5, which says x equals 5 halves. This one I set equal to 0, x plus 1 equals 0, says that x is negative 1. So my x-intercepts are 5 halves, y equals 0, and negative 1, y equals 0. So I've got 1 y-intercept, 0, negative 5. I've got 2 x-intercepts, 5 halves, 0, and negative 1 comma 0. Okay. Now I want to figure out the vertical asymptotes. Well, again, I make sure my numerator and denominator don't have any common factors. So that numerator factors into 2x minus 5 and x plus 1. But they're trying to trick us here. X squared plus 1 is something I cannot factor. If this were x squared minus 1, I could factor, because that's the difference of squares. But this would be the sum of two perfect squares. That's not factorable. So since there is no place where that denominator will ever be 0, then this thing has no vertical asymptotes. So there are none. there are no vertical asymptotes. My denominator will never be 0. I can't factor x squared plus 1. Okay? I can't do it. So there are no vertical asymptotes. Well, now we want to talk about maybe horizontal asymptotes. Horizontal asymptotes. Okay. Well, for horizontal asymptotes, the degree of the numerator is the same as the degree of the denominator. So that means I have a horizontal asymptote. I take the ratio of the two leading coefficients. There's a 2 in front of x squared in the top and a 1 in front of the x squared in the bottom. So my horizontal asymptote would be the ratio of those two coefficients. So y equals 2 would be my horizontal. 2 divided by 1 is 2. That's my horizontal asymptote. Now, it turns out that functions will never cross a vertical asymptote, but a function can potentially cross a horizontal asymptote. Okay? Functions never cross vertical asymptotes, but they can cross horizontal asymptotes. So the question becomes now is where does the function cross the horizontal asymptote? I want to know, where does the function cross the horizontal asymptote? Well, the horizontal asymptote is y equals 2, and the function is y equals this, so y equals that, and y equals 2. So to find that, all I got to do is set the equation equal to it. Y equals 2, set it equal to 2x squared minus 3x minus 5 over x squared plus 1. So I'll say y equals 2 equal to y equals that. Solve this equation, and then I'll have the x values that show me where the function crosses the horizontal asymptote y equals 2. Now again, all functions don't cross horizontal asymptotes. But if it does, then I'll be able to find these x's that satisfy that. If I can't find x's that satisfy this, that means that my function does not cross my horizontal asymptote. So I want to solve this thing. And again, to solve this, I'll cross multiply, because if I want, this is the same thing as 2 over 1 equals that over that. So cross products are equal. So 2 times x squared plus 1, 2 times x squared plus 1 would be equal to 1 times this stuff, so 2x squared minus 3x minus 5. Distributive property, 2x squared plus 2 equals 2x squared minus 3x minus 5. If I subtract 2x squared from both sides, those two things cancel, right? Subtract 2x squared from this side, subtract 2x squared from that side, then they cancel, okay? So I'll have 2 equals negative 3x minus 5. Add 5 to both sides, 7 equals negative 3x. X equals negative 7/3, okay? X equals negative 7/3 should be where we cross our horizontal asymptote. Okay, x equals negative 7/3. Let's see. Just want to make sure we're coinciding. Okay. So we did vertical asymptotes. Which one am I doing? 2x squared. Oh, I'm doing this one. I'm looking at the wrong problem. I'm sorry. So again, I crossed my horizontal asymptote at negative 7/3 when x is 2. So where I crossed my horizontal asymptote, the x coordinate is negative 7/3. The y coordinate was y equals 2. That's where I'll cross my horizontal asymptote. Okay. Now, since the degree to have a slant asymptote, right? So now let's say number 5. Slant asymptote. Well, you'll have a slant asymptote when the degree of the numerator is exactly 1 more than the degree of the denominator. But these two degrees are equal, so there are none. There are no slant asymptotes, there are no vertical asymptotes. We have only a horizontal asymptote at y equals 2. Okay? So we figured out our horizontal asymptote. We figured out that we don't have any verticals. We don't have any slant asymptotes. We did have a y-intercept of 0, -5. We've got these two, x-intercepts. So now I probably am at a point where I just want to try to grapple it. Okay? I want to try to grapple. Okay. So let's flip this over. Let's see if we can graph this thing. So again, you'll get your y-intercept, your x-intercepts, your asymptotes. Again, a function can cross. It may or may not cross a horizontal asymptote, and it may or may not cross a slant asymptote. Okay? This thing didn't have any slant asymptotes, so I didn't need to check that. But you check it the same way I checked that it would cross the horizontal asymptote. You set the two equations equal to each other. That's how you always check to see if two things cross. So let's plot what we know, okay? Let's plot what we know. We've got our y-axis and our x-axis, okay? And we had a y-intercept at 0, let's see, y-intercept was 0, -5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 5. Okay, so we had a y-intercept of 0, -5. Right here. We had x-intercepts at 5/2, 0, and -1, 0. 5/2 is 2.5, so x and y-intercept there. We didn't have any vertical asymptotes. We didn't have any slant asymptotes. We had a horizontal asymptote at y equals 2. Okay, there's our graph of that. Okay. Now, I also knew that my function crossed my horizontal asymptote at -7/3, 2. -7/3, right? 3 goes into 7, 2. So this is -2 1/3. So -2 1/3, 2. So that's where I cross the horizontal asymptote. So I really don't have a choice with this stuff. It's got to do this. But again, maybe I don't know what goes on over here or over here. Well, check some points. So do your t-chart. And maybe let's check x equals -5. So my function, f of x, was 2x squared minus 3x minus 5 all over x squared plus 1. So I just put a -5 in here. So f of -5, everywhere I add an x, I put a -5. I got a squared here, minus 3 times -5, minus 5, all over -5 squared plus 1. Well, -5 squared is 25, positive 25. 25 times 2 is 50. -3 times -5 is plus 15, minus 5, all over. -5 squared is 25 plus 1, 26. Okay? All right. So take your calculator and do this. All right. So this will be 65 minus 5 is 60 over 26, right? 50 plus 15 is 65. 65 minus 5 is 60 over 26. 60 over 26. Take your calculator and do that. That's a little bigger than 2. I'm going to call it 2.1. So -5, 2.1. So this thing is going to come up, and it's going to come and just get lower and lower and lower, and get closer and closer to that dashed line, but never cross it again. You can only cross a horizontal or a slant asymptote once. It will never cross it again. So it's going to go above it, and it's going to level out and just go that way. Over here, it didn't cross over here because the only crossing point was right here. So the function has to just do this and just get closer and closer and closer to that line, never touch it. So there's a graph of that function. So this is how we'll graph these rational expressions. We're going to find the y-intercepts, x-intercepts. We're going to find vertical, horizontal, slant asymptotes. We're going to find out if it crosses the horizontal or the slant asymptote. Okay, it will never cross a vertical asymptote, but it might cross a slant or a horizontal asymptote. And we just saw how to do it. If it crosses the line y equals 2, then set the equation equal to y equals 2, and then solve. That's the same way you'll do the slant asymptote. So that's how those problems work. So that's section 2.5. We're in 2.6. 2.6 is polynomial and rational inequalities. 2.6, polynomial and rational inequalities. So read these sections. You should always be reading your book. Okay, polynomial and rational inequalities. So now we say inequalities. Okay, before we had an equal sign. So now we'll have an inequality. So we'll have things like less than or equal to, greater than or equal to. So for example, let me just take one out of the homework, so it'll be nice. 5x times x is 5x squared. You'll see things like solve. 5x squared. Okay. Minus 25, minus 28x. And then plus 15. Okay. And you might see that thing less than or equal to 0. And they ask us to solve that. Again, this used to be an equal sign, and we knew how to solve those. That's a quadratic, right? We'd apply maybe the quadratic formula if we wanted to, or we'd factor, or we can complete the square. We had a bunch of ways to solve this. But now we got to understand a couple of things before we start solving these things. Well, when I solved an equation, don't worry about this one for now. Let's consider 2x plus 1 equals 0. If I want to solve that, I'll subtract 1 from both sides. Look at that. Then divide by 2. There was my only solution. Compare that to this. 2x plus 1 less than or equal to 0. Now I'll subtract 1. Divide by 2. This thing though, x is less than negative 1/2. If I think about where negative 1/2 sits on the number line, the real number line, that means everything's smaller than that. So the solution to this, the solution to that equation was a single number, negative 1/2. The solution to this inequality is anything in the interval from negative infinity to negative 1/2. Now, since I got less than or equal to, it's going to be a bracket there. So this would be the solution to the inequality. So the solution to equations were individual numbers, right? If it was a linear equation, x to the first, I get one number. If it were a quadratic equation, if this were equal to 0, there'd be two solutions to that. But now that it's an inequality, the solutions will be an entire set of numbers. If you pick any number out of this set, x equals negative 10, for example. 2 times negative 10 would be negative 20 plus 1. That's negative 19. Negative 19 is less than or equal to 0. Take x equals some other number out of here. Say x equals negative 3. X equals negative 3 lives in this interval. Put a negative 3 where the x is. 2 times negative 3 is negative 6. Negative 6 plus 1 is negative 5. Negative 5 is less than or equal to 0. So there's a whole infinite set that satisfies that inequality. Okay? So the solutions to equations used to be numbers, but the solutions to these inequalities are going to be infinite sets of numbers. Okay? The solutions to these inequalities will be infinite sets of numbers. Okay? So that's the first thing I got to realize. Now, there's a second thing I need to realize. I need some paper. Okay? there's a second thing I need to realize, and in order to save paper, I'm going to use this little corner. Let me just show you one other thing I got to be careful about. 2 is less than 3. Okay? So we're going to have inequalities like less than, or less than equal to, greater than equal to. 2 is less than 3, right? If I think of the real number line is like this. There's 0, there's 1, there's 2, there's 3, there's 4, there's -1, there's -2, there's -3, etc. 2 is less than 3. But if I divide by -1, and if I do it over there, I'm going to do it like there. I get -2. Positive 2 divided by -1 is -2. 3 divided by -1 is -3. Okay? Now, this used to be a less than symbol between these two numbers. Then I divided both of them by a negative. But now what goes between them? Is it still less than, or is it now greater than? Well, I know how the real number line works. It gets bigger as I go to the right. So any number that's to the left of another is a smaller number. For example, 2 is smaller than 3. 1 is bigger than 0, or 0 is less than 1. -2 is less than -2. -3 is less than -2. So 2 was less than 3, but when I divide both sides by a -1, that inequality changed direction. 2 is less than -3, but if I divide by -1, -2 is now greater than -3, because -2 is sitting here, -3 is to the left of it. As I go from left to right, I get bigger. So -3 is smaller than -2, -2 is smaller than -1, -1 is smaller than 0, 0 is smaller than 1. I get bigger as I go that way. So -2 is greater than -3. So it's going to be really important to realize, and this is going to be a really important point. Whenever it's going to be you multiply or divide by a negative number, you must change the direction of the inequality. That's what we're going to have to remember when we solve these polynomial inequalities now. Whenever I multiply or divide, either one, here I divide it, but it's the same thing if I multiply. Whenever you multiply or divide by a negative number, you have to change the direction of the inequality. This used to be less than, but after I divide it by a negative, it becomes greater than. Okay? If I had a second one that said that -5 is greater than -10, right? That's a true statement. Multiply both sides by -1. Okay? That gives me a +5, and that gives me a +10. -5 was less than -10, but 5 is now, or -5 is greater than -10, but 5 is now less than -10. So whenever I multiply by a negative or divide by a negative, that direction of that inequality has to change. Okay? That's what we have to remember. Okay. So that's going to be the most important thing when it comes to these polynomial inequalities that I have to remember. Whenever I perform either multiplication or division by a negative, I'm going to have to change the direction of that inequality. That's the only time though. Whatever else I do is fine. I can still add and subtract numbers to both sides. I can multiply or divide by a positive number that doesn't change the direction of the inequality. It will be only when I multiply or divide by a negative number. That's when I'll change the direction of the inequality. Okay, so let's do example 1. And they tell us how to do this. There's some step-by-step is on page 323. The step-by-step process. It's page 323. Read it. Read it. I want you to make sure you understand all those steps in that process. So let's just do one. Example 1, solve the inequality. So I'll solve the inequality. They give me 3x times x minus 1, okay, greater than 10 minus 2x. 3x times x minus 1 greater than 10 minus 2x. So take a look at that step-by-step process. It's on page 323. I'm not going to write it down, but make sure you read it. So the first thing they say is we've got to make sure we have one side that's 0. Okay? We got to make sure we have one side that's 0. So I'm going to distribute here. 3x times x is 3x squared. 3x times negative 1 is minus 3x. That's greater than 10 minus 2x. Now I'm going to get everything on one side because I want a 0 on this side. So I'm going to add 2x. And I'm going to subtract 10. So add 2x and subtract 10. So I get 3x squared. Negative 3x plus 2x is minus 1x. And the minus 10 is here. And now I'll have greater than 0. Okay? So I subtracted, or I added 2x to both sides. And then I subtracted 10 from both sides. So now I've got one side 0. This is always how you want to be. You want this left side in descending powers of the variable, 3x squared first, then x to the first power second, then the number third, and then whatever the inequality is, greater than, less than equal to, greater than equal to, and then 0. You always want one side to be 0 before you try to solve the inequality. Now, factor this side completely. Factor this side completely. 3x squared is 3x and an x. How do you get 10? Well, 10 could be a 2 times a 5, or it could be a 10 and a 1. A 2 times a 5, excuse me, or a 10 and a 1. So I'm going to use the 2, I'm going to use the 5. And this is going to be negative, that's going to be positive. So there's my factorization. You can check it if you want, FOIL it out if you want. But that's how it factors. So 3x plus 5 times x minus 2 gives you 3x squared minus x minus 10, okay? Well, and again, FOIL it out if you want. 3x times x is 3x squared. Outer product is negative 6x. Inner product is positive 5x. Negative 6x plus 5x is negative 1x. Positive 5 times a negative 2 is a negative 10, so I know it works. So now they say solve as if you had an equation. So pretend like it's not an inequality anymore. Pretend like that was an equal sign. That's what step number 2 says in that step-by-step. So make sure you've read this step-by-step process. That's really important. So make sure one side 0, descending powers of your variable, factor completely. Then pretend like it's an equal sign. So now, a product equal to 0 means either 3x plus 5 equals 0, or x minus 2 equals 0. Subtract 5 from both sides. Divide by 3, you get x equals negative 5/3. Here you add 2 to both sides, x equals 2. These are called boundary points. Boundary points. And what these numbers do is they separate the real number line into intervals. They separate the real number line into intervals. So there's 0, there's 1, there's 2, there's 3, there's 4, negative 1, negative 2, negative 3. X equals 2 sits right here. X equals negative 5/3. Negative 5/3 is negative 1 2/3. It's about right there. Okay, there's negative 5/3. So these two boundary points separate the real number line into 3 intervals. There's an interval over here from negative infinity to negative 5/3. There's the interval between negative 5/3 and 2. Okay, so the 3 intervals or negative infinity to negative 5/3. This interval would be negative 5/3 to 2. This interval over here goes from 2 to infinity. Okay? So these are the 3 intervals. Now again, the boundary points are exactly where this function is equal to 0. Okay? The boundary points are exactly where it's equal to 0. What I want to do is I want to figure out, what I'm going to do is I'm trying to solve this. This is what we're trying to solve. I want to know where this thing times this thing is greater than 0. Well, greater than 0 means positive. If something is greater than 0, it's positive. If something is less than 0, it's negative. So I want to know where this thing times this thing is positive. Okay? So what I'm going to do is I'm going to look at these, and again, the product this thing is going to be positive. I need to figure out the signs of each one of these two factors. I've got a 3x plus 5 factor and an x minus 2 factor. I'm going to look at each one of those factors in this interval from negative infinity to negative 5 halves and figure out if this thing is a positive quantity or a negative quantity. Then I'm going to look at this factor, figure out if it's a positive or a negative quantity in that interval. Then I'm going to move to the second interval and figure out if this factor and this factor is positive or negative in that interval. Then I'm going to move to the third interval and figure out if this thing is positive or negative and this thing is positive or negative. So I'm going to test the function in each one of the three respective intervals to figure out if it's positive or negative. And again, if this thing is positive and this one is negative in that first interval, then a positive times a negative would be a negative. That's not greater than 0, because again, I want to know where the product is greater than 0. Okay? So, with that in mind, I'm going to try to maximize my use of my paper. Okay? So again, I'm going to take this first interval. The first interval was from negative infinity to negative 5/3. Okay? And I'm gonna need a test point in each interval. And actually, I want to do it this way. First interval is negative infinity to negative 5/3. Second interval was negative 5/3 to 2. And the third interval goes from 2 to infinity. Okay? So, this is where I want the test point. And then I'm going to look at the two expressions, 3x plus 5. And I'm going to look at x minus 2. Then I'm going to look at the product. Okay. And again, I wanted to know whether that product was greater than 0 or positive. That's all I care about, whether the product of this factor and this factor is positive. Now, what do I mean by a test point? Well, I want to figure out if 3x plus 5 in the first interval from negative infinity to negative 5/3. I just want to know if it's positive or negative in that interval. Same thing with x minus 2. In this interval, negative infinity to negative 5/3, I want to know where it's positive or negative. Okay? So that just means I need a test point out of that interval. So pick any number that's in this interval. Well, we looked at this. This was 0, negative 1, negative 2. There's negative 2, there's negative 3. So if you want, negative 3 would be a good test point in that interval. Okay? And all you're doing is putting the negative 3 where the x was. 3 times negative 3 is negative 9. Negative 9 plus 5, right? Negative 9 plus 5 is negative 4. So the thing is negative in that interval. Okay? A good test point in negative 5/3 to 2. So from negative 5/3 to 2, 0 is in there. So 0 is going to be my next test point. So I take 0, I'm putting that in for x. 3 times 0 is 0. 0 plus 5 is a positive 5. So this factor is positive in that interval. Then I take a test point in the interval from 2 to infinity. Well, what about x equals positive 3? Put a 3 where the x was. 3 times 3 would be 9. 9 plus 5 is 14. That's positive. All I'm doing is figuring out for this factor only whether he's positive or negative in each one of these respective intervals by choosing a point in that interval, plugging it in, and see if I get a positive or negative quantity. I'm going to do the same thing with x minus 2. The test point in the first interval was negative 3. Put a negative 3 where x was. Negative 3 minus 2 is negative 5. That's a negative quantity. Negative x minus 2 in this second interval, the test point was 0. So put a 0 where the x is. 0 minus 2 is negative 2. That's a negative quantity. In the third interval from 2 to infinity, the test point was positive 3. X equals positive 3. Put a 3 where the x was. 3 minus 2 would be a positive 1. So he's positive there. Okay? Now again, I wanted to know where the product of these two things was greater than 0 or positive. Greater than 0 means positive. So something times something needs to be positive. Well, I've got it made now. So in this interval, this factor is negative. This factor is negative. So a negative times a negative would make a positive. The whole product of the two, right? This thing times this thing, that's that expression we wanted to figure out. This times this, I want to know where it's greater than 0 or positive. Well, this thing is negative in this interval. This factor is negative in that interval. So a negative times a negative times a negative is a positive. Well, in the second interval from negative 5/3 to 2, I want to know this factor times this factor. So a positive times a negative is a negative. A positive times a positive in that interval is a positive. So again, I wanted to know if the product of the two was greater than 0 or positive. So they're positive in this interval, negative infinity to negative 5/3, and that product is positive in this interval from 2 to infinity. So the answer, the two intervals is positive in this interval, negative infinity, negative 5/3. Union, it's positive in this interval, 2 to infinity. So that would be the answer to that problem. Okay? So that's how we're going to solve these polynomial inequalities. We're going to draw a chart. First, we're going to find, this was our process. The first thing we did was get everything on one side, descending positive variable, there's my inequality sign, and there's a 0. That's always the first step with these problems. Okay? Then I factor this thing completely. Okay? And after I factor it, I solve each one of those two individual equations to find my boundary points. Place those boundary points on the real number line. I had a boundary point at negative 5/3. I had a boundary point at 2. So these two boundary points separate my real number line into 3 intervals, from negative infinity to the first boundary point, then the interval between the two boundary points, negative 5/3 to 2, then interval from 2 to infinity. Those two boundary points separate the real number line into 3 intervals. I'm going to take those 3 intervals, put it here, here, and here. I'm going to find a test point in each one of these intervals. It never matters what point. As long as that x value exists in that interval, is fine. I could have used x equals negative 100 if I wanted. In this interval from negative 5/3 to 2, I chose 0, but I could have chose x equals 1. I could have chosen x equals negative 1. I got lots of choices. And then I choose an x in this last interval from 2 to infinity. I chose x equals 3. I could have chosen x equals 100 if I wanted. Wouldn't have mattered. There's my test point. I take that test point and put it in the first expression. Replace x with negative 3. 3 times negative 3 is negative 9 plus 5. That's negative 4. That means that this expression will be negative in that entire interval. If it's negative for that one test point in that interval, it's negative for all points in that interval. Then I take the test point 0 and put in that same factor. 3 times 0 plus 5 is a positive 5. So that thing is positive in the second interval. Then I take the test point 3. 3 times 3 is 9. 9 plus 5 is 14. That means that it's positive in that interval. Then I check the second one, and then I do the product, because I have the product of the two factors. So a negative times a negative makes a positive. Positive times a negative makes a negative. Positive times a positive makes a positive. That's how I solve these polynomial inequalities. Okay? That's how we're going to solve these polynomial inequalities. Okay. All right. Let's do another example. Okay. Let's do another example. All right. Let's do example. And they show you the graphs of these things. Okay. They show you the graphs of these things if you want to look at that. All right. I'm going to go ahead and skip a couple of them. Let's do example 3. Solve. They say they say 4x squared minus 12x plus 9 less than 0. 4x squared minus 12x plus 9. 4x squared minus 12x plus 9. And they say less than 0. Okay. So I've already got it in the right form. Descending powers of a variable. There's a 0 on the other side. Okay. That's always where you want to start. Okay. Well, can I factor this thing? Can I factor this thing? Well, I think I can. Get a 4x squared, that's 2x and 2x. Get a 9, that's a 3 and a 3. That's a negative, that's a positive, which means that both of these are negatives. So really, I could have written it like this. All right. So now I'll solve as if I had equality. Okay, pretend you got equality because I'm finding the boundary points now. Well, take the square root of both sides and you'll just get 2x minus 3 equals 0. 2x equals 3, x equals 3 halves. So that's my boundary point. Boundary point. Okay. Once you find the boundary points, now again, let's put that boundary point on the real number line. So there's 0, 1, 2, 3, negative 1. 3 halves is 1 1/2. So he sits right here. 3 halves. So that separates my real number line into two intervals, negative infinity to 3 halves, and then from 3 halves to infinity. I've got two intervals to check. So now, again, I wanted to know where the product of those two was less than 0. Okay, so we're trying to find out where 2x minus 3 times 2x minus 3 is less than 0. That's what I started out. This thing squared, that times that itself, less than 0. So I'm going to create the same little chart. So first interval was negative infinity, 3 halves. Second interval is 3 halves to infinity. So I need a test point in each. Test point. So in this interval, I can choose 0. I like 0 because things go away. So then I got 2x minus 3. The other factor is 2x minus 3, 2. Then it's just 2x minus 3 times 2x minus 3. Okay? So take 0. That's the test point in here. If the interval from 3 halves to infinity, this interval, I can choose x equals 2. So my test point there is 2. So put a 0 where the 2 is. 2 times 0 would be 0 minus 3. So that means that that thing is negative in this whole interval. Again, if it's negative at the test point, this test point is in that interval, that means that this expression will be negative for that entire interval. Okay? Put the 2 in there. 2 times 2 makes 4. 4 minus 1 is a positive 1, so the thing is positive there. Well, that's the same factor, so it's negative and positive here. So that factor times itself, a negative times a negative, means that this product is positive in this interval. A positive times a positive means that this product is positive in that interval. Well, I wanted to know where he was less than 0. Well, it's positive in the interval from negative infinity to 3 halves. It is positive in the interval from 3 halves to infinity. It's 0 at the boundary point. The boundary point was exactly where it was equal to 0. So this thing is never negative in that interval. Okay? So part A, if you want, you can write the empty set. And that's your answer. Because there aren't any places, there aren't any x values where this thing is ever negative. It's never negative. It's positive in that interval, positive in that interval. Well, B says, same equation, 4x squared minus 12x plus 9, but this time less than or equal to 0. So 4x squared minus 12x plus 9 less than or equal to 0. Well, again, less than 0 would never happen. It never happened. It was positive. It's the same function, so it's, all of this will be the same for it. 4x squared minus 12x plus 9, 4x squared minus 12x plus 9. The only thing that's changed is that instead of less than 0, I had less than or equal to 0. So it's positive in the interval from negative infinity to 3 halves. It is positive in the interval from 3 halves to infinity. So it's never less than 0, but it could be equal to 0. It was equal to 0 at the one boundary point. So for part B, that would be my answer. That function is never less than 0. But it is actually equal to 0 at x equals 3 halves. So the solution to where this thing is less than or equal to 0 will be the one point, that one boundary point, x equals 3 halves. Part C. C says 4x squared minus 12x plus 9 this time greater than 0. Well, again, I go to my chart. Now again, it's equal to 0 at 3 halves. But now I want to know where it's positive. Well, this product, 2x minus 3 all squared, is positive in the interval from negative infinity to 3 halves. It is positive in the interval from 3 halves to infinity. Again, it's equal to 0 at the boundary point. So from negative infinity, 3 halves, union, 3 halves to infinity. that would be the answer to part C. It's positive in this first interval. It is positive in that second interval. And finally, D, 4x squared minus 12x plus 9 greater than or equal to 0. Well, again, it's greater than 0. We just did that. It's greater than 0 in this interval and this interval. That's the entire real number line, just taking out the 1.3 halves. But the or equal to 0 is greater than 0 in these two intervals, but it's equal to 0 at the one boundary point. So if I take the infinite interval from negative infinity to 3 halves, plus the interval from 3 halves to infinity, and I add back in that one missing boundary point, then now it's greater than or equal to 0 for all real numbers. Because again, part C, this set plus this set, the only thing you're missing on the real number line is the 1 point, x equals 3 halves. So since it said greater than or equal to 0 now, you're adding back. It's equal to 0 at the boundary point. You're adding that 1 point back in, and hence it'll be greater than or equal to 0 for the entire real number line. Okay? That's how that works. Okay? All right. Let's do one more. Let's do one. These. Okay. Should be the last sheet of paper we need. So let's do maybe example 5. Solve. 1 over x minus 2. They say greater than or equal to 1 over x plus 3. 1 over x minus 2 greater than or equal to 1 over x plus 3. Okay. Well, again, we always said we wanted 0 on one side, so I'm going to subtract 1 over x plus 3, and I'll get this. We always want 0 on one side, so all I did was subtract 1 over x plus 3 from both sides. Now I'm trying to subtract fractions. To subtract fractions, you got to have a common denominator. The common denominator, the LCD, would just be the product of x minus 2, x plus 3. So I've got an x minus 2 in my denominator, but this is the one I want. So to get the right denominator, I'm going to take 1 over x minus 2. I'm going to multiply it by x plus 3 over x plus 3. X plus 3 over x plus 3 is 1, so I'm not changing anything. Minus, I've got a 1 over x plus 3. I need a denominator of x minus 2 times x plus 3. So I'm missing the x minus 2, so I'm going to multiply this with my x minus 2 over x minus 2. Okay? And I've still got this greater than or equal to 0 part. Okay? So when I do this, 1 times x plus 3 gives me x plus 3, and then minus. I got to be careful. That minus sign is going to apply to this whole thing, so minus x minus 2. I've got the same denominator now. So now I've got that. 1 times x plus 3 is x plus 3 minus 1 times this stuff minus 1 times this stuff. But again, I got to put this in parentheses because that minus sign has to hit both terms. So I'll use parentheses. And I've got the same denominator now. X minus 2 times x plus 3, x minus 2 times x plus 3. The order doesn't matter. Multiplication is commutative. So let's go ahead and do this. So x plus 3, negative 1 times x is minus x. Negative 1 times negative 2 is plus 2. Okay, x minus x goes away, and I get 5 over okay, got that. Okay, now there's my simplified inequality. Okay? And I said I need, first step is always to find the boundary points. So the boundary points, I can find those by solving the equality. I'm going to set it equal to 0 to find the boundary points. Okay? I'm going to set it equal to 0 to find the boundary points. Okay? Well, so now how do I solve that thing equal to 0? Well, to find where this thing is equal to 0, I'll multiply both sides by, I need to get rid of the fraction, so I'm going to multiply this one times x minus 2, x plus 3. And on the other side, I'm going to multiply by x minus 2, x plus 3. These cancel, I get 5. And on this side, 0 times that stuff is 0. So I get 5 equals 0. 5 equals 0 is a contradiction. Okay, so that means that there are no solutions to that equation. There are no solutions to that equation. So that process won't help me. That process won't help me. Okay, so I need to figure out where, again, this divided by that is greater than or equal to 0. Okay, so I didn't get any additional boundary points from that process, but I can kind of look at, this is my real problem. I'm trying to solve this thing. I want to know where that quotient is greater than or equal to 0. So I can actually still use that chart. Okay, I can still use the chart. All right, because again, greater than or equal to 0 means either equal to 0, and equal to 0, I didn't have any solution. Right, there was no solution here. So that just says there's no points where there are no boundary points. There's no points where this thing is equal to 0. So all I really care about now is I need to figure out where it's greater than 0. Okay? Equal to 0 didn't work. There was no solution to when it was equal to 0. So I don't have to worry about that equal to part. Now I'm just trying to find out where this quotient is now greater than 0. Greater than 0. So keep that in mind. Keep that in mind. Okay? All right. So we're going to do that this side. Actually cheat this time, since I take the tape long enough. All right. So I'm trying to figure out where 5 over x minus 2x plus 3. That's what I'm really trying to figure out. Okay? Now, the boundary points from this thing, again, I don't have any boundary points, but I know that I had these vertical asymptotes, right? 2 minus 2 makes 0 in my denominator, right? So that's one interval. Negative infinity to, so there's two places. Negative 3 plus 3 would make 0, right? Negative 3 plus 3 would make 0. So there's an interval from negative infinity to negative 3. Then I'll have the interval from negative 3 to 2, because 2 minus 2 makes 0. Then 2 to infinity. So those are the three intervals that I'm going to be looking at. Okay? The interval from negative infinity to negative, and I found these intervals because of these two zeros in the bottom. X equals positive 2 and x equals negative 3. Okay? And I can put those on my number line just to make sure we're clear. So 0, 1, 2, 3. Okay, so I had a 0 at negative 3. Negative 3 plus 3 makes 0. And I had a 0 at positive 2. So that's why I said the intervals are negative infinity to negative 3. That's this interval. Negative 3 to 2. That's this interval. 2 to infinity. That's that interval. Okay, so those are my intervals I'm going to be looking at. Okay, and I'm going to take a test point in each. In this interval, I'm going to use x equals negative 4. In this interval, I'm going to use x equals 0. In this interval, I'm going to use x equals 3. So, I had a 5 And in this interval, 5 is going to be positive. In this interval, 5 is positive. 5 won't change, right? I've got 5 over this stuff. But the 5 is going to be positive, positive. 5 is positive 5. It stays positive in any interval on real and y. Okay, the other factor I've got is x minus 2. I take my test point -4. -4 minus 2 is a -6. Take a test point 0. 0 minus 2 is a -2. Take the test point +3. 3 minus 2 is a positive. Right? Then I take the factor x plus 3. Okay? Test point was -4. -4 plus 3 is a -1. Test point 0. 0 plus 3 is a +3. Take the test point +3. 3 plus 3 is a +6. Now look at what I'm doing. I'm taking 5 divided by this times this. So a positive divided by a negative times a negative, right? Because the two factors in the bottom. So in the bottom I'd have a negative times a negative makes a positive. So a positive over a negative times a negative is a positive over a positive or a positive. Because this is the whole thing right here. This one would be a positive divided by a negative times a positive. So in the bottom, a negative times a positive is a negative. So a positive over a negative makes a negative. In this one, 5 over a positive times a positive, that's a positive. Well, I wanted to know if this thing was greater than 0. It's greater than 0 in this interval. Okay. Union, it's greater than 0 in this interval, 2 to infinity. That would be your solution set. Okay? That would be your solution set. So that's how these problems work. Okay? That's how these problems work. That's how we solve these inequalities. If you have any questions, please let me know.